Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, today in this particular lecture, we will going to discuss about frequency of spread spectrum systems. So these are the outlines. We'll start up with the introduction. Then we will discuss what is FHSS system, how basically it works, which will be followed by the principle behind FHSS system. Then we will discuss FHSS transmitter followed by receiver. Then we will going to discuss two variants of FHSS systems, that is your slow hopping frequency of spread spectrum system and fast hopping frequency of spread spectrum systems. They are the classification which is based over dwell time. So we will discuss on that, what is dwell time and how we are going to define what is fast hopping frequency of spread spectrum systems and what are slow hop frequency of spread spectrum systems. Then we will be going to discuss several advantages as well as the disadvantages of the frequency of spread spectrum systems, and finally we are going to conclude by discussing some of the applications of FHSS systems. Spread spectrum modulation spreads the spectrum of transmitted signal into the wider range, makes the signal very robust to unintentional interference or jamming. So this is, we have already understood in our previous lectures that in spread spectrum modulation schemes, what we are actually going to do is we will going to spread the spectrum of the transmitted signal so that they will become very robust to the jamming. So the types of spread spectrum modulations are frequency of spread spectrum system. In FHSS system, transmitted signal keeps randomly changing its carrier frequency. So what is actually happening in this particular scenario is the central carrier frequency will keep changing on, it will not fixed, just like as in our traditional narrowband communication system. And second variant is your direct sequence spread spectrum systems. In DSS, transmitted signal is represented by the wideband code. We actually expand our narrowband signal with the help of PN sequence codes that we had already discussed. So this code transforms narrowband data into the noise-like signal, or we could say that noise-like wideband data. So in both types of spread spectrum techniques, we basically require a noise-like code which is used to enhance or increase the bandwidth of our signal. So basically in both the variants of spread spectrum communication system, somehow we are utilizing or using a PN random sequence generator. With the help of that random sequence, we are actually trying to enhance or increase our transmitted signal spectrum. So how we will going to enhance or increase spectrum of our signal in direct sequence spread spectrum system, we had already seen in our earlier lectures. So now we will try to focus that how with the help of PN sequence generation, we will going to enhance or expand the transmitted signal bandwidth in FHSS system. So in our last lecture, we have discussed about DSS system, where we find out that there is a limitation of processing gain in DSS system, as we cannot increase the value of n beyond the certain limit. So where n is the number of bits in the chipping code, we cannot increase the value of n, that is number of chipping bits that lie in a bit duration due to certain pulse width limitation. So this limitation restricts the performance of the direct sequence spread spectrum systems. Since we know that the processing gain is nothing but it is the ratio of expanded signal bandwidth divided by the signal bandwidth without expansion, and the bandwidth of the expanded signal is dependent upon the value of n, that is number of bits in the chipping sequence. So if we cannot enhance or increase the value of n beyond certain limits, then obviously it will going to restrict or limit the processing gain in my DSS systems. So in this particular lecture, we will going to discuss about frequency of spread spectrum system, which provides the better processing gain. So what is frequency hopping spread spectrum system and how it actually functions? So it is the spread spectrum technique where center frequencies get changed periodically according to the PN sequence. So here what important point I'm going to make is, here the central carrier frequency is not fixed. It is keep on changing periodically, and at what instant which frequency it will going to take or which carrier frequency it will going to opt in order to transmit its signal, that is totally dependent upon PN sequence, which is random. So for modulation purpose, we could use coherent or non-coherent, any type of modulation techniques such as our MFSK, that is your multi-frequency shift keying, as well as binary phase shift keying, etc. So any sort of modulation techniques would have been exploited in our FHSS system. So signal is broadcast over seemingly random series of frequencies. This is what we had already mentioned, that here central carrier frequency is not fixed, it is keep on changing. So basically we will going to broadcast our signal over random series of frequencies. So receiver hops between frequencies in sync with the transmitter. So transmitter and receiver, both of them are in complete sync, so that they should know at what instant of signal transmission which carrier frequency would have been used for transmission. So eavesdropper, if somehow gets the access to the user data, can only hear unintelligent blips. So suppose in this particular scenario where the central carrier frequency is keep on changing, if any eavesdropper or unintended user somehow gets some information about the central carrier frequency, it is not getting the complete information, it is only getting an unintelligent smaller portion or unintelligent blip of the signal, or we could say that small portion of the input signal, which is not sufficient enough to find out the complete information. So jamming on one frequency affects only a few bits corresponding to that frequency only. So in jamming also, if some user try to jam certain frequency band, so it will only going to jam that much amount of signal which is centered around the jamming frequency. So it will not going to affect the complete amount of information. It could only affect only smaller portion of our transmitted signal, whereas rest of the signal can be easily transported. So this particular figure is showing the principle of FHSS system. So on the y-axis we will be having several frequencies, and on the x-axis we will be having time. So what we are actually doing is we have actually divided this complete wideband spectrum into 8 parts, 1, 2, 3 up to 8. Then what we'll be going to do in our FHSS system is, at initial stage our signal is transmitted with the help of this central carrier frequency F5. Then after some time it will going to take another central carrier frequency which is equivalent to your F1. Then after another certain time interval it will going to take another central carrier frequency that is analogous to your F4, and then after some time it will going to take the central carrier frequency F8, and so on. So what we or actually wanted to mention at this particular point is, the central carrier frequency is not fixed, it is keep on changing. First we are using F5, then F1, then F4, then and so on. In our FHS system, our central carrier frequency will not going to fixed as in our traditional communication system. It will keep on changing, as we have already seen that at certain moment it is your F5, then after some time it will going to take central carrier frequency as F1, then after some time it will going to take the central carrier frequency F4. So what I wanted to mention at this particular point is, our complete signal is being distributed over this entire wideband spectrum. It is not confined or fixed to over a certain frequency band. That is why we are saying that our signal bandwidth has been expanded, since it is containing the complete range of frequencies. So this is how we will saying that our signal bandwidth has been expanded. So this is the basic principle of our FHSS system. So now in this particular slide, let us discuss a comparison between frequency division multiplexing and frequency of spread spectrum system. So what we are actually doing in our traditional FDM system is, we are actually dividing our complete frequency spectrum band into subbands, and then we will assigning a particular subband to an individual user. Suppose in this particular example we have divided our complete frequency spectrum into 4 subbands, and we are assigning to these frequencies F1, F2, F3 and F4 analogous to different users, and users are using only those subbands to transmit their own information. So any two users will not going to use the another user's frequency band, which will going to cause certain amount of interference. Each and every individual user is bound to transmit in its own subband, and that frequency band is available to that particular user for the whole time. So in contrast with your FDM, what we are actually doing in our FHS system is, here also we are dividing the complete frequency spectrum band, but here we are not restricting that any user will going to only use a single frequency band. Obviously it can use any sort of frequency band, but provided it should not produce any sort of interference to the transmission of other users. as we can see in this particular scenario, that at this particular moment, suppose user 1 is using this F1 frequency, user 2 is using this F2 frequency, user 3 is using this F3 frequency, and user 4 is using this F4 frequency. So after some time, user 1 will going to use the user 4's frequency, and user 4 will going to user 3rd's frequency. So obviously this can be possible if we can keep on changing the carrier frequencies, and this is what we are actually doing in our frequency of spread spectrum system. So now from this particular example, we could understand that each and every user's data would have been present in all of the frequency bands. So this is how we could say that, in contrast with our traditional FDM system where the single user channel bandwidth is only confined in one subbands, in our FHS system, single user's data would have been distributed over the entire frequency band. And this is how we are saying that the transmitted bandwidth of our signal in FHS system has been expanded. So now we're going to discuss frequency of spread spectrum transmitter. So initially we'll be having data bit, which is denoted by our DT, which will going to pass through the frequency modulator or BPSK, whose another input is the carrier signal, that is your A cos 2 pi FCT. Then this modulated signal will get passed to the product multiplier, which is also being called as frequency hop spreader, whose another input is the carrier frequency CT, which is the outcome of your frequency synthesizer circuitry. So what frequency synthesizer circuitry is? It is a basically electronic circuitry which can be able to generate the different frequency signals. So this frequency synthesizer circuitry is taking the input from the channel table, and what basically the channel table is having several bit sequences as the index, and for every index it is having a table of different frequency values. Just like for 000 it is having 200 kilohertz, 001 it is having 300 kilohertz. So for different index value it is containing different frequency values, your F1, F2, F3 up to F8. So channel table is getting the input from our pseudo noise bit sequence. What is pseudo noise bit sequence generator? We had already discussed. It is basically generating random bit sequences. So here we are assuming that it is actually generating 3-bit output sequence, which is random. So it is basically randomly generated 3-bit sequences, and depending upon the output of our PN random bit sequence, it is basically selecting any frequency bands from its channel, and that selected frequency information would have been passed to the frequency synthesizer circuitry, which will going to generate the central carrier frequency depending upon the information it is getting from the channel table. So what our FH spreader is actually doing is it is providing certain product multiplication with the SDT signal and CT signal, and then this modulated signal, or we could say that the spreaded signal or expanded bandwidth signal, will get passed through the band pass filter, which will going to take the sum frequencies, and that spread spectrum signal ST will get passed through the channel. So here is the explanation about FHSS transmitter. So initially the binary data are fed into the modulator using the FSK, your frequency shift keying, or binary phase shift keying. So we could use any one of them. So the resulting signal SDT is centered on some carrier frequency. So obviously DT is passed to the product multiplier, whose another central carrier frequency is A cos of omega CT. So that signal will get centered around that carrier frequency, which is your modulated signal. So a pseudo random number serves as an index into the table of frequencies. This is what we are mentioning in our last slide, that pseudo random number generator serves as the index. So it is basically providing some index value, and for each and every index value, several set of frequencies would have been assigned in our channel table. So depending upon the input of that index value, our frequency synthesizer circuitry will going to select the actual carrier frequency, and it will generate the carrier frequency CT, which will be keep on changing depending upon the input from the PN sequence generator. So each k-bit of PN source specifies one of the 2k carrier frequencies. So obviously if we are assuming that our PN sequence is of k-bit, then the PN source specifies one of the 2 to the power k carrier frequencies. So in our last example, what we have taken, the value of k is 3. So the different value that would have been selected with the use of 3 bits, that will be equal to 2 to the power 3, that is 8. So 8 different values would have been selected, or we could say that we can have 8 different values of carrier frequencies, and at a particular time it will going to select only one carrier frequency. So at each successive interval a new carrier frequency is selected. This is what I have explained. So the frequency synthesizer generate a constant frequency tone whose frequency hops among a set of 2 to the power k frequencies with the hopping pattern determined by the k bits from the PN sequence. So obviously the frequency synthesizer will going to generate one of the carrier frequency at certain duration of time, and when another bit sequence would have been generated by the PN random sequence generator, it will going to switch over to the next carrier frequency. So the hopping pattern, that is from one central carrier frequency to another central carrier frequency, which pattern it will going to take, that would have been determined by the PN random sequence generator, which is random. So this is known as the spreading or chipping signal, CT, of the FHSS signal. So this alternately varying carrier frequency signal would have been called as your chipping signal, that is your CT for FHSS. So this signal is again modulated to produce the new signal with the same shape, but now centered on the central carrier frequency. So obviously if the value of CT would have been changed continuously, it will going to generate the signal which is centered at the central carrier frequency CT at that particular moment. So band pass filter is used to block the difference frequency and pass the sum frequency, yielding the final FHS signal, your ST. So obviously it will going to contain two sort of frequency component, as we had already discussed in our modulation process, that it will going to generate two frequency component. One is sum frequency and another one is the difference frequency. So where both the frequencies will going to have the same amount of signal, so we are selecting here the plus or sum frequency. So now we're going to discuss one example of frequency hopping. So this particular plot is showing between frequency and the energy. So again we have divided our complete frequency spectrum into 8 parts from F0 to F7, as we had already discussed in our last example, where we have divided our complete spectrum into 8 parts. So since we have started with F0 or F0, so here also we have divided them into 8 parts. So last part is our F7. So these sub channels F0, F1, F3, F4, these are certain equally spaced frequency subbands, and this is actually showing the output of our PN random sequence generator. Suppose initially it is generating 101, then in the second cycle it is generating 111, then in the third cycle it is generating 001. So depending upon that value, it will going to select the central carrier frequency. So just an example, let us consider that the decimal value of 101 is equivalent to 5 and 111 is equivalent to 7 and so on. The last 100 is equivalent to decimal value 4. So depending upon the outcome, it will going to select the central carrier frequency. So here we could say that for the initial transmission of our signal, we are using this F5 carrier frequency. Then we will going to switch over to our F7 carrier frequency. Then after some time we will going to again switch over our central carrier frequency to F1, then F0, then F2 and so on. So on this right side figure, we are trying to show this particular sequence, that how we will going to generate frequency hopped signal. So initially when we have to initiate our transmission, our central carrier frequency would have been selected as F5. Then after some time, the next central frequency that we will going to select is our F7. Then in the third cycle we will going to select F1. Then in the fourth cycle we will going to select F0 and so on. So this is how our FHSS signal would have been generated, whose central carrier frequency is keep on changing, that at certain moment initially it is your F5, then F7 and then F1. So that sequence, that from F5 to F7, then F7 to F1, it is completely random in nature, which is governed by the outcome of your PN random sequence generator. So this is how the single user data would have been distributed in the entire frequency spectrum, or we could say that we have generated a wide band signal from the narrow band signal. So this is the example of our frequency hopping. So now we're going to discuss frequency of spread spectrum receiver. So the input to the receiver is the spread spectrum signal ST that is passed through the FHSS D spreader. Since at the transmitting side we will be having frequency of spreader, so at the receiving side we will be having FHD spreader. The second input to the FHD spreader is again the CT, which is the same carrier frequency as we have used at the transmitting side, and this CT would have been in complete sync with the transmitter side CT. So this CT signal would have been generated with the help of frequency synthesizer circuitry, which will going to take input from the pseudo random noise bit sequence generator. So what I wanted to point out at this particular moment is this CT and CT that we have generated at the transmitting side, they should be in complete sync so that the receiver should know that at which particular instant which frequency it must have to generate in order to obtain the information signal. So the output of FHD spreader signal would have been passed through the band pass filter, which will going to generate our SDT signal, which will further pass through the demodulator circuitry. Depending upon whichever type of modulator mechanism we have applied at the transmitting side, that is whether FSK or BPSK, we must have to pass our signal SDT through the respective demodulator, whose second input is the carrier frequency a cos of 2 pi FCT. So it will going to generate our binary data sequence DT. So this is the explanation what we have discussed so far. The spread spectrum signal is demodulated using the same sequence of PN derived frequencies and then demodulated to produce the output data. This is what I have discussed, that there should be a complete sync between the transmitter and the receiver side PN sequence, so that they could operate over the same frequency bands or same chipping sequence CT. At the receiver, a signal of the form ST defined on the previous slide will be received. Then this is multiplied by the replica of the spread signal to yield the product signal. So this is actually being showing the operation of our FHD spreader. So one input to our FHD spreader is the actual signal ST, which will get multiplied with the CT. It is basically maintaining the same carrier frequency information as we have at the transmitting side. The output of our FHD spreader or frequency of D spreader will be the product of our signal ST with the CT, which will again get passed through the band pass filter. So band pass filter is used to block the sum frequency and pass the difference frequency, which is then demodulated and recover the binary data. So this is how our frequency of spread spectrum receiver will functions and retrace the same data bits DT as we have generated at the transmitting side. So now we will going to discuss the two variants of frequency of spread spectrum system, that is slow hop frequency of spread spectrum system and fast hopping frequency of spread spectrum system. So before we will going to discuss what are they, let us discuss few basic terms in order to understand the fast hopping frequency of spread spectrum system and slow hopping frequency of spread spectrum system. Hop time. What is hop time? So it is the small amount of time during the frequency change in which no transmission takes place. So as we had already discussed in our example, our central carrier frequency will keep on changing. That is, for certain moment of time, it is transmitting central carrier frequency F1. Then after some time, it will going to transmit over another central carrier frequency F5. So hop time is the small time during the frequency change from F1 to F5. And please keep in mind here no signal transmission will going to take place. It would have been considered as the switching time from one central carrier frequency to another central carrier frequency. Then what is dwell time? So it is the time spent on a particular channel with the carrier frequency. So we could also say that it is the time duration over which signal is transmitted over single central carrier frequency. So if I would have to explain it with the help of certain figure, then let us say at initial time interval central carrier frequency F1 is selected and user is transmitting its information using that central carrier frequency F1. Then after certain time it will going to move on over next central carrier frequency. Let us say it is equivalent to or analogous to your f5. So the time gap in which no signal is actually being passing, this time lag is actually called as your hopping time, which would have been represented by your th. So hop time is the amount of time during which frequency changes and no transmission actually have been take place. So this is your hopping time. And what do you mean by dwell time? It is that time duration in which signal is only using a single carrier frequency, that is equivalent to f1, or we could say that f5. So this dwell time is represented as Td, and this is the actual duration. So on the basis of dwell time, we can talk about two variants of FHSS. So I mean, if the value of Td is greater than bit duration Tb, or the value of dwell time Td is less than the value of Tb. So first variant is slow FHSS. So what basically slow FHSS is? It means many of the symbols would have been passed, or many of the data bits would have been passed on the same carrier frequency. That means hopping or changing among the central carrier frequency is quite low. So this would have been called as your slow FHSS. So that is your dwell time is greater than your bit duration Tb. So it means many of the bit would have been passed through the same carrier frequency, or hopping rate is quite slow. So the transmitter remains in one frequency band during the transmission of multiple bits. This is what I wanted to explain with the help of this relationship. So the example of slow frequency of spread spectrum system is our GSM. The exact value of dwell time in GSM is 4.2 milliseconds. So in slow frequency hop spread spectrum system, multiple bits would have been passed using the same carrier frequency. Whereas in the fast hopping frequency of spread spectrum system it is basically just the inverse case of your slow hop frequency hopping spread spectrum system. That is, here in this particular case, your dwell time Td is very much less than Tb. It means for transmitting a single bit or symbols multiple times, carrier frequencies would have been changed. So the transmitter hops in many frequency bands during the transmission of single bit. This is what I have tried to explain you. So the example of fast hopping frequency of spread spectrum system is Bluetooth, where the dwell time is 1600 hops per second. It means in a single second, 1600 times your carrier frequency will get changed. So this figure is actually showing the example of our slow hop frequency of spread spectrum system and fast hop spread spectrum system. So in this upper portion of our figure, it is actually reflecting the user data. So user data is your 0, 1, 0, 1, 1. Actually high value of pulse is representing 1 and low value of pulse is representing 0. So this is your user data, and the bit duration is represented by this value Tb. So please keep in mind, this is just to show the example of your fast hop frequency of spread spectrum system and slow hopping frequency of spread spectrum system. This is not the standard one. So let us assume that in a single dwell time, this Td, we are transmitting 3 bits, that is 0, 1 and 0. So and after that, this dwell time, we will again going to switch over to next central carrier frequency. So during this dwell time Td, we are actually passing 3 bits amount of information, or we could say that we are actually passing this 3 bit amount of information using same central carrier frequency. So this is the example of your slow hopping frequency of spread spectrum system. That is, we are passing 3 bits per hop, or we could say that we are passing 3 bit amount of information over the single central carrier frequency. Whereas in the second figure, what it is actually showing is, here this Td, dwell time Td is quite lower. So in figure, it is also being clear that Td is very much lower in comparison to your Tb. So in order to pass this single bit amount of information, our central carrier frequency will get changed 3 times. That is, for certain duration of time, the central carrier frequency is f1, then for certain duration of time it is your f3, and for certain duration of time it is your f2. So central carrier frequency will get changed 3 times in order to transmit single bit information, that is your TB. So we could also say that it is our fast hopping, or we could say that our central carrier frequency is changing very fast. So in this particular example, we are actually changing the central carrier frequency 3 times in order to transmit 1 bit information. So this is actually showing the fast hopping frequency of the spread spectrum system. So now the advantages of FHSS system. The synchronization is not greatly dependent upon the distance, as it is the case for our direct sequence spread spectrum system. Here we have seen that if the distance between the transmitter and receiver is much more, the synchronization will get affected due to the multipath propagation effect. Then the serial search system with FHSS needs shorter time for acquisition. So here the acquisition time is quite lower, obviously, in comparison to our direct sequence spread spectrum system. We can acquire the frequency information much faster. And the third advantage is the processing gain of GP is higher than the DSSS system. So in DSS system, we have limitation over the chipping duration. We cannot exceed the value of GP or processing gain greater than N, where capital N is the number of bits in the chipping sequence. But in the FHS system, we can increase or enhance the value of processing gain considerably higher. So now the disadvantages of FHS systems are: the bandwidth of FHS system is too large. As I had already mentioned that we could enhance or increase the value of processing gain. So the bandwidth of FHS system is too large. And the second disadvantage of FHS system are complex and expensive digital frequency synthesizers are required to be used, since synthesizers are the major functional blocks of your FHSS systems. So obviously from hardware point of view, we are requiring such sort of synthesizers which could generate a variety of central carrier frequencies quickly and efficiently. So that is why we need some expensive and complex frequency synthesizer circuitries. So here are some of the applications of our frequency spread spectrum system. That is, they would have been used in WLAN standards 802.11b. They would also have been used in Bluetooth technology. For data transfer, we would have been using this FHSS spread spectrum communication techniques. They would also have been used in single channel ground and airborne radio systems. And walkie-talkies are another example of our FHSS system. These are the references. Thank you very much for your patient hearing.